Hello, this is Silvia, and I wanted to show you a quick demonstration of these additional fiber sections that I've added to eSEES. These are meant to do some analyses of walls. These are fiber sections, so I think they're very handy to study the materials and the wall sections as components, doing some sort of moment curvature analyses of the sections themselves. You can, and I will show you how, you can just put them into a tall building. But it's really important to keep in mind that for a lot of tall buildings, most of the inelastic action occurs at the base, which means that you don't want to have such busy fiber sections along the entire height of your building, because that just becomes computationally expensive. I'm going to do a simple example, so I'm not worried about that. My personal time in determining the elastic properties is a little bit more expensive right now than just sending my computer to run and doing its analyses. So here's a little demonstration of the different sections that I have built. I'm going to open up a file that I have already worked with just to get things set up a little bit easier. What I've done is I've defined a series of materials and a series of cross sections and some simple elements in a simple 3D cantilever type of system, but I'll walk you through. So what I've done is I'm going to go into the input. I'm going to look at the materials. As much as I've defined a heck of a lot of materials, what I've done is defined a concrete material, which is actually, I've called it the model confined concrete, and I'm using concrete 07 just for fun. If you want, you can change it to concrete 02, any other sort of material. So this is what my confined concrete looks like. For my unconfined concrete, what I've done is I just use concrete 01. So if you look under concrete 01, I have it here, or I actually have what I call unconfined concrete right there, which is one of the materials that I've predefined, and I think it's based on concrete 02 actually. It's nice to have a little bit of tension strength there. I already defined the material properties just at 4.4 KSI. All I did was just use the default properties. So these are my two concrete materials, and then I've also defined my steel, and I believe it is I love my multilinear steel, so here it is the Reinfoced-Concrete steel material. So this is what the steel material looks like in my walls. I'm just going to assume they all have the same concrete across all the different flanges and webs of my walls. This is what the behavior looks like up until the strain level. If I increase my strain levels, it gives you a better idea. This is the hysteretic material, so I don't have any degradation of the envelope, but it's a nice and inexpensive material that's very reliable and converges very well, and it's just faster than most of the other materials. So these are the three basic materials I'm going to use in my cross sections. So what I've done is I've defined, and I'm going to show you here in the new, if you go to the fiber components, I've defined these new components: a rectangular wall, a T wall, a left corner wall, a right corner wall, a C wall, which is a U-shaped or C-shaped wall, as well as a box wall. So because they have so much input, I've already built these in my script. I can show you the script actually, but I will do that after I've shown you what they look like. So here's my rectangular wall. You select it, and this is what the geometry looks like. You can define all the different dimensions of the different boundary elements to be different. You can give them offsets. For example, right now, while the center would be at this point here, I actually have an offset of the global system to be this way, so it's not quite centered in my structural system. And then if you want, I can offset my flanges, if you something like this, just to show you. You go here, you fill in, and it shows you, I offset it a little too much maybe, so why don't we just offset it by 6 inches. So this would be a way of making a wall that looks like this. And if we test it, this is what now this wall looks like in the behavior. I don't know if it really made too much of a difference. This is about the horizontal axes, and then this is about rotated about the vertical axes. And you could see it has different behavior. It's funny because it almost looks stronger in this direction, but if I copy these data and I test it in the other direction, it's just more brittle. And if I paste that force deformation response, you see how much stronger it is in bending about the horizontal. Then this is pretty much the behavior of this system. You can play with the number of bars, the size of the bars, and as you can see, this little thing here just kind of gets updated real time. This is for a rectangular wall. I've also done a T-wall. This is what the T-wall looks like. It takes a little bit, my computer's real slow these days. This is what the T-wall looks like. It's all any sort of these little parameters you can play with, and I highly recommend. It's just kind of fun to play it and test it out. The other wall I have is a left corner wall. And if I haven't covered these sections, I would love to, get some ideas of what the different wall configurations are for simple walls. I'm then going to work on building a template so that you define all these different regions instead of having a predefined template for each one of them. But that requires a little bit more work on the user end. This is the other corner wall. I then have what I call a C wall, because it's not fully closed. And this is what the C-shaped wall looks like. If I copy these data and I test it in the rotated direction, probably won't see too much of a difference, but it's not as symmetric. And you can see there it is, a lack of symmetry in that direction. And then the last one is a rectangular box, what I call a box wall. It's kind of cool because I've tried to make as much flexibility in the configuration. Of course, somebody's going to want something different. This is rectangular, but this you can actually move these webs to the left or to the right. I have labels. You kind of got to, when you work with these walls, even though they're drawn in this direction, you kind of got to tilt your head 90 degrees to the right, because I see this as the left, the right, the top, and the bottom. I had sketched these out by hand. That way they make a little bit more sense when you're working with a T-wall, but I always like to have the Y vertical. And that's pretty much that for the wall sections. You can see these are the response. You can always copy these data and paste them to wherever you want to do some post-processing. What I then also have is I've put these into an elevation, and then I've put them into a 3D model. So if I go straight to that, and I've done some cyclic pushover, I kind of want to show you the behavior of this type of model. So here's a simple wall that actually has 4 elements. This is the rectangular. Yeah, let's do the rectangular. This is a C shape. So the rectangular is just the fastest one. So here's a rectangular wall. You can visualize it. You can show the axes. Here's what the components look like. This is actually the C wall. I'm going to view the rectangular wall. This is what this looks like. Yeah, I do have to improve my graphics here. So this is that wall there in 3D. I'm going to subject it to some cycles in the X direction, and then I can analyze it. I click analyze, and it'll take a little bit and run through the analyses. Once I've run the analyses, and I've already done it for a number of these, so let's look at the most interesting one, which is a rectangular wall actually in the X cycles. This is what, as you can see, is just a 4-element model. If I look at my bending moment diagrams, I believe you have to do it. Oh, I like to draw it on the tension side. There it is. This is at a time step, so you can pick this time step here. You could scale the diagram if you like. And maybe it's not about the Z, maybe it's actually a moment about the Y. There's your moment about the Y, here's your values. What I want to do is I want to have a look at this column right here, the very first floor. You can look at moment rotation, because I use some concentrated plasticity elements. So if I plot this here, I should have some response, because most of my inelasticity is at the base of this wall. And then, so there it is at node I and node J. If I want to do a fiber section analysis of this and look at the strains across the section. And what I've done is, instead of plotting strains, I plot strains as a function of time, and you pick which location in your cross section you like to be. So it takes a little bit of time to run the analysis because it's a complicated section. All right, here's what my section looks like. You pick your material. You could be the concrete 01. I'm interested to see what happens to my confined concrete, and you pick the location of your fiber. So at this end, you'll see that you have this is the stress-strain relationship at the history at that point. I assume at this point is going to be different, and yet it's symmetric, so it's actually going to look exactly the same. If I look at my steel, and these are just points that I've kind of predefined for my reinforcement, just kind of corner points where it's defined. And it seems like most of the response comes from the concrete. But sometimes if you get more interesting structures, so maybe if we look at a C shape, oh, let's look at the T wall. That's for sure going to have something interesting. Ah, there it is. Yeah, this is a good one. So let's go here. If we look at the fiber response here, definitely have some stuff happening, but likely it's more the concrete. I literally just came up with numbers that are just random, so it's not a well-defined section. The axial loads are just random, but I try to make something until they give me something nonlinear. Here's what my section looks like, and so now I'm going to close this one to not distract ourselves. So let's look at the steel. That's some strain. The first one is always some random value that is pulled out. Oh, look at that. That's one of the steel at one of the extremes. So let's look at this extreme. So that's what's happening in that reinforcement. At this reinforcement over here, we've got this type of behavior. If we look at the reinforcement over at this end. And so it's kind of fun. Let's look at what the concrete has done. Let's look at the confined concrete. And so what's happening to my core concrete in the different regions. So this is all in tension at this side pretty much. If we go kitty corner from there. I don't think I clicked the right number. Okay, there it is. And I guess there's some symmetry there. Let's look at in this direction. I think I'm loading it in this other direction. So, and this is what's happening to the concrete. It's mainly in the compression, in the tension side of the world. So this is just a nice demonstration. Let me find the interesting. This is Concrete 07. I got to go to Concrete 02. Just a much more reliable material. But it's also a good way here testing the materials that you're using and see how reliable. There's just way too much going on in this Concrete 07. I think I'm going to switch over to Concrete 02 and see what happens and rerun this analysis. So how do I do that? Well, I go here, and remember how I said I use the same material for all of them. So what I can do is I go to my material and I edit my confined concrete. So I think I was using Concrete 07 for my model, right? So if I go here and I say I don't want to use Concrete 07, I actually want to use Concrete 02. Or just the confined, this is literally Concrete 02. I use just 4.4. I'm going to test it, see what happens. There's a nice stress strain. I'm going to save that. And now I'm going to run the analyses again. So I'm going to analyze my T wall. So it's in alphabetical order. Here's my T wall. I'm going to load it in the, I believe I was loading it in the Z. So I'm going to say, okay, run the analyses here. And you got to be careful. Down here, this is the plan view. So this is looking from above. And because there's no dimensions in this, it's literally a point, it's really impossible to scale what's going on there. So that's, you always have to be careful in these visualizations because they're pretty much automatic. This is the two axes. You can see here that we're loading it in the Z, and it is moving in the Z direction. While it's doing this, what I could do is I can load up my input file and show you what the input file looks like. So here's my input file. I'm going to just make it not too big so that we can actually keep track of what's going on there. And what I've done is, this is the input file in eSEES. It's just very simple. It's text here. What I need to do is I changed it in the GUI, but I'm going to actually change it here on the script where my model concrete, and this was because I initialized all my materials, so I just have a huge list of materials, even my PY springs. But here's the steel model, and I'm going to try to find, there it is. So this is my confined concrete. Instead of saying concrete 07, I'm going to do concrete 02. Or I think I had, doesn't matter. I'm just going to stick with concrete 02. You can save your input in eSEES in the GUI, but then you wouldn't be able to keep this kind of formatting that I have here in defining my model, where here's my pushovers, and then these are all the different sections, and you see those are all the different properties of the seawall and all the properties of that. But then what I have is I have a loop that I say, okay, for 4-story building, this many stories, and I do it for each one of those model types or each one of those cross sections. I build an elevation, and then I stick an elevation to the grid. If you save directly from eSEES, you're going to get everything written out and you lose your loop. So I like to start off my program using the user interface, but then I always like to go back to my script and just work mainly in scripts. So I'm going to pause my speaking here, let the analysis run, and start up again when the analysis is run. Remember, in eSEES, it takes a little bit of time to also process the analyses. So whenever this changes to back to analyze, then the program is ready for you to go. It has moved to 3 cycles, first to 1/2 inch, then to 1 inch, then to 5 inches. You can see this 5 right here. Now we're going to do 3 cycles to plus or minus 7 inches. And this is in the Z direction. You see deformations here. Again, don't worry about the scale on the left-hand side. And here it is. We do see this is just very rough data, but I like to keep it just to watch the structure deform. We're going to go all the way to minus 7 inches. How do I know that? Well, that was the input that I gave it in the program. If you look at, these are the cycles, full cycles in the X and the Z. I went to 1, 5, and 7. Oh, I didn't do half an inch. In the Z I did 0.5, 1, 5, and 7. And that's what you see there. And 7 inches is not that much. It's hit that, but you can see we've definitely lost a lot of strength in that direction. Mainly that's where it happened in this other direction here. Don't worry about the signs here because I'm plotting pseudo time versus displacement, but it's a good indicator that the structure is moving. So we're going to do a total of 3 cycles, so 2 more cycles to plus or minus 7. The analysis is complete because you can see it's back to saying analyze here. What we want to do is we want to look at the results, but the first thing I like to do is I look at the output from OpenSees, and here's the output of the analysis. It's in that little window that we set aside, and we go from a 0.4 second period, 0.35 to 2 seconds. There's definitely some softening. Barely any convergence problems. It literally just took a long time because I should have picked much smaller time steps. So this is a really good way of looking at the results. And then if we go graphically, we click results, it's going to go with the latest analysis that we did. And if you want, we can plot the bending moment diagram. Remember, it's at this time step. So I'm going to pick this very high time step. Maybe I will scale the deformations a little bit so it looks like it's deformed. I'm going to scale the diagram a bit more. And I'm going to do bending moment diagram in the Y on the tension side. And maybe there is no bending moments in that direction, so let's do it in the Z. There it is. So that was the direction that we loaded it. And yes, I could have asked for the different local axes. But here's bending moments that we're looking at, and so this is the section that we want to look at because it's got the highest deformations. And if we do, it's doing a moment curvature analysis on this. It takes a little bit of time, and then I will show you the response of that. So it's going to take a little bit of time to run the moment curvature analysis because there's a heck of a lot of fibers. And look at this. Now we've got something that makes a little bit more sense. If I go to that concrete material, and I think it was at this section here, maybe it will look exactly as it looked before. But yeah, it's a little bit cleaner than what I had there with all this tensile that shouldn't really be there. So if we look at the extreme fibers, let's see what we find out. And I could have saved the previous data, but here's data that makes just a lot more sense. I like concrete too. I know it's kind of strange that you've got tensile strength in that direction, but it's a much more reliable material. So this is the concrete. Let's look at the steel. Interesting stuff going on. So this was a good study on material study as well, not just what these sections look like. And that's it. I hope you have some fun learning a little bit more about concrete here. I had to find out why I don't have the recorders here, and there's always something new that I find out about my program. Anyways, I hope this helped. Bye-bye. If you want to get your own copy of eSEES, which I would recommend, of course, and it would really help to support the project that I'm doing, you can go to my website, which is sylviasbrainery.com. You'll find links everywhere, or you can even just put sylviamazzoni.com. It will take you here. You can go to shop, and there's even eSEES. There's a little description. There's some videos on YouTube, and here's some demonstrations. This demonstration is going to be here. You can get a professional license, academic license, and the student license. Prices are pretty low right now because it's an introductory offer. They've definitely gone up since the beginning of this project. Give me some feedback, and I hope you purchase this program so that you can support what I'm trying to get done. Thank you. Bye-bye.